Say hello. Good evening, everyone.
Good evening.
Hello. Yeah,
Good
good
evening,
evening.
sir.
Okay, I'll share my screen and we can start. So today will be yeah, good evening, Rito. Welcome back. Mm, Okay, I'll share my screen. We can start. Yeah. Okay. So this is what we'll cover is mostly from week 10 and 11 uh, as a revision session. So we'll cover RNN, LSTM, GRU, uh, and encoder-decoder, right? And if there is time, I'll also cover attention, right? So if I cover attention, then 10, 11 will be over. We'll be able to, I guess, complete it. So okay, so I'll start with RNN. Okay, so let's say we have sentences like I sat on a chair. Okay, this is a sentence, and I have to predict the next word. If I give I, then the prediction would be set, and if I give set, then the prediction would be on. So this is my kind of say uh, train and test set you can make. So if I give one hot vector of this I somehow, then it should predict set, right? So that is the problem that we are dealing with, and we want to predict the next word. Next word prediction is the task here, right? So this is a sequence. First, this problem is sequence to sequence, right? Uh, so here sequence is important. Like uh, I can't give something like a different like bag of words or something like some words I throw up and then I expect it to output, right? So a next word has so much dependence on the previous whatever I have given, right? So otherwise the sentence meaning could change, or there is no meaning at all, right? So rubbish output, then that's what I don't want. I want it to have a good output, and I want to predict the next one. That is the idea. It's a sequence to sequence problem. So to handle this sequence, we have created this RNN. Uh, and what we'll do is, so first see what is the architecture of RNN. Okay, so let's say this five words are there, and I do one hot encoding with them, and I have 1000, right? So this is you can say I, uh, okay, and then 101000. That is another one set, and so on, right? So you get the point that I'll write one for a number like somewhere in the index, and that will represent some word, right? So this one of the words will be represented by one hot vector, right? So this is one hot vector. Okay. Now so this is what my input is. I have to give. I have to predict the next word, right? So I'll create a, that's a neural network which has, let's say, or yeah, let's say, so this is my neural network, and this can take so this is my input layer. Okay, as of now this is my input layer. So if I wanted to send I will give one here, 00 everywhere else, right? So this will be my input. So this is my input layer, and I need something here as a hidden layer, right? So that hidden layer, let's say this is my hidden layer, which contains 3 neurons. Okay, and what you will do is you'll do the natural thing, like send the inputs here and like that, right? So this will this I will call as um this I'll call as u, right? So this is my u matrix, which will contain all these vectors. Sorry, all these weights, right? So weights are being represented by u, and I'll call this input as x, right? So my input I'm calling as x, and I'm sending whatever weights are there between input and the hidden layer are called u. So what will be the dimension of u here? What do you think? Dimension of u. Um,
Cross three.
3 cross 5, right? So I'll have 3 rows and 5 columns. Okay. Uh, and that's what it is. So that's my first word. I've sent it, and it will produce some kind of output. I'll send it through softmax layer, right? So softmax layer will be the next layer. Like you can take 4, 5, whatever you want, but generally what we do is we whatever we have given, like in that form I want, right? So I have sent 5 words, so I want that many. You like unless you have another words, like let's say Hindi to English translation, something like that problem will come up. So that's where you can choose different kind of softmax uh, neurons, right? So here I need 5 of them too. Uh, so how many are this? Are there going to be weights in between? I'll call this weights as V. Uh, 5 cross 3, right? So this is my 5 cross 3 weights, and this is what a neural network looks like. If I would have stopped here, it looks like ANN. Nothing I'm doing different than this, and you can say this is kind of SIBO or skipgram also. True. So here comes the next part that will not stop here. Will connect something from previous layer, right? So whatever outputs I'm getting here, you can call it as let's say h, right? So h1, the vector, the complete vector is h1, or it's good to call s1, s, right? S1. That I'll send it to itself, right? So this is my neural network, uh, or look like. Now at so you can say this is a time step t equal to 1. Okay. One part is I haven't given any s0 to it as of now. But I'll give it like so consider I'm going to do next. Same thing I would have done for S0. Okay, so this is my S1. Now what I'll do is uh, okay, so this is my another timestamp. So here the thing only changes is timestamp, right? So this is a timestamp equal to 2. Okay, and it will produce S2 here. Okay, produce S2. Now what I'll do is I'll give whatever I got from previous this thing output. I'll give it to neurons as well. So hidden layer will get 2 things. If I can, yeah. So this hidden layer will get 2 things. Like okay, so all of them, right? And again with the second also to all of them. Okay, and same thing with the third output also, and like this, right? So all of them are going to all of this, and this is at the time step 2. And it producing S2, and of course I will do predictions. I'll get y hat here also, y hat here also. You can call it y hat 1, y hat 2, whatever, something like that. So you get it that now if I go to S3, and of course I have to given here, I would have given x1, and I'll give x2 here. Okay, same thing. So this is what how RNN looks like. Now I'll not draw this again and again. So what we do is we can create this box. I'll call it as RNN. uh, and or maybe just RNN block like it. This is how it like, and we can say X is going from here. S0 or ST-1 is coming from here, and and it will go to another one, right? So little louder down, little small. So X1 is going from here, S0 would be coming here. So see here, I didn't give S0, but what you can do is you can create a three size, a vector of size 3 uh, with some random values. So random values would have worked, okay, and you have to give it. That's all. So initially you will do that, but after your model will train, it will uh, it will learn, right? So initial first step you have to do it, or you can give zeros also, no issues. 0, 1, anything. We'll see. We'll do something better with S0 later on when we'll go to encoder, decoder, and all. But as of now, you can randomly initialize and not do anything about it. Okay. So here I am producing X1. This I'll send it to my let's say here, and I'll produce output from here, right? So this weights are going to be here V. I'm calling this as U, and here I'm calling as sorry, W, right? So this is how it's working. This is a softmax layer. This is a sigmoid you can take, okay, all of them like this, okay, and this is how now I'll represent as RNN, okay. This is how RNN will look like. So what will be the equation of RNN? So first you have to produce this S1, right? So this will produce S1. So this S1 will be produced by, let's say, sigmoid is the neuron I'm using, and I'm using UX plus you can take UXT plus WST-1 plus some bias I can use. So some biases here will be there to each of this neuron, and that I'm giving as B, right? So this is how you will produce S1 or ST, if I can say ST, right? So that's what I'm producing, and then I'll use to predict this last softmax, right? So this YT will be produced by some softmax, right? So softmax uh, of softmax of we have to use VST. So ST is coming out also, and then it's going to predictions also, right? So both the ways S1 is going, like same thing. Just you have to use it at the both ways. So you have to send it to the next output, like this, like yellow thing here, and it will of course go to this red neurons, which is softmax layer, right? WXT, and I'll use some kind of bias again here for this another set of neurons, right? So first I have to do reactivation, and then I'll do activation, like I used to do in softmax layer in ANN. Same thing, nothing changes, and this is how we get the RNN structure. And you get the idea. Like now it's 2. You can go up to any numbers, 3, 4, 5. Same thing you have to do. So this next guy, so whatever S2 is produced here, it will go to the next one, right? Like this, like let's say I have one is sigmoid, right? So S0 will come, W are the weights, X1 is coming, U are the weights, and it is producing S1, and of course W weights, then it will go to the next layer, right? So again I'll give X2 here, so the next one, right? So I'm giving here I, and here I'm giving set. Again the weights are same, so nothing like weights will not change because we are using same architecture to again and again do this, right? So that's what the recurrent part is, that I'm doing this. This is this yellow part, the yellow lines are recurrent connection, okay, and so on, right? And of course I'll do predictions at every time step. So this I'll call as Y1, Y2, and let's say for the sake of it I'll do X3 on, and I'm not doing for all of them, but you get it, that this is where it is Y3, right? And here I'm going to give S1 as well as new weights B and C also, S2 and V, S3 and V, EU. Okay, right. So this is how the architecture is. Now we have to do back propagation. So that is the idea, that we have to do back propagation. So before that, what is the loss going to be, right? So loss is something if we know the loss, we can do the back propagation. So so output is softmax, and we'll use loss as cross entropy, right? So we'll use ln summation of from I to k classes, right? Uh, y true, and then log of y hat. So this is what we do, and you have seen that I've used uh, one hot vector for this, right? So again, uh, this some of this terminology, some of these terms will go away, and finally you will get some yk, right? Like here, like sorry, yi should be yi. Some y will you will get, right, at each time point. So mostly so it should be negative also. So this some at k or I equal to L, you will get this, and you have to do back propagation for that. So this is what equation is. Now the part back propagation about us till okay. So how many weights I have to update us? I have to update U, I have to update V, I have to update W, and B and C, right? So this five kind of weights I have to update. The most easiest one in this is this V part, right? So this is the easiest part, and C also. Both are same thing, like nothing much changes here. So V and C are the easiest one, because we have you can say Y hat is equal to this soft max of V ST plus C, right? So this is the equation of Y hat, and if I have to do like I used to do in ANN, I can do it, right? So if I do dl by V, then it will be loss with respect to Y hat. Then Y hat I'll do with respect to whatever that summation is, right? So internal summation like AL or something like that we call like pre-activation. So this is what I'm calling as pre-activation, and then AL I have to do with V, right? So this three terminology will come. So the summation is what I'm calling as AL. Okay, if you don't remember AL, the summation is what I'm calling as AL, and the summation I'm taking derivation with respect to V. Okay, and these three terms, if you solve, you will get the derivatives with respect to V at each stem, right? So this is for, let's say, uh, term 3. Then you have to do same thing with t equal to 2, same thing you have to do with t equal to 1, and you'll get three kind of thing, and you have to sum them, all of them. So that is all total cross entropy, right? Total loss, basically you have to find total loss, you have to sum all of them, and you can get it. That's how you get the total loss, and then back propagate it. So you have to back propagate till, so from all of this, right? So uh, this guy will back propagate, this guy will do, and this is also there, right? So all three will go, and you have to sum also while doing back propagation. Okay. Now, is there any doubt here? Because next part is little difficult. If you don't get it, then I don't. Uh, okay. Um. Okay. I think you get it. So now I'll not do with C. Same thing you have to do with C, like this, and then you'll get it. Now we'll do with respect to W, right? So let's do with respect to W here first, like and if I show you with respect to this third thing, from here till the W, then I guess you can do for all of them, right? So second component, then third, first component, and you can do it, right? You just have to sum them. But if you know the third, I guess all of them are okay. So okay, Now let's see. So so from here I would have predicted loss. Okay. And if I have to go back, I'll first go to y3, y3 hat. Then I would go to s3. Then from s3 I have to go to this w, right? So w is here with respect to this w and s2, right? So I have to go to uh, s2 here, and then I can do it, right? So if I write this much as of now, then that would be dl by y hat. Then y hat, from that I went to s3. Then s3 is the guy which is connected to w, right? So you can see here, if I write st, you can see here s3, then it will be ux2 ux3 plus ws2, right? So here one component of w is there, so I'll do that tau s3 by tau w, right? That I can do. Now the thing is, if I go this way and not this way, then the issue is I'm not doing the proper back propagation, right? Because in S2 also there is W component exists, right? Like here, it exists here also. So I have to go further back to for this, right, to get this uh, gradients. Okay, so I reach as of now till S, uh, kind of say W, this W I reached, right? So this W you can say I reached. Now from S3 I have to go to S2. So this part you can say here I got here. Now I'll go a little bit further. Like from S3 I have to go S2. From S2 I can go to W. And same thing I'll do uh from S2 I have to go to S1. And from S1 I have to go to another W. So this kind of thing will appear. So what I'm saying is that this was one component, and the another is I should go from S3 to S2. Then from S2 I can get another W, right? So this part is another, and in S2 by W, that is another catch, that it should be tau S2 by uh, S3 by S2. S3, yeah, sorry. S2 I reach, then from S2 W, and then one side is S1, right? So that would be, should not be just this much. So whatever this multiplication is, I have to write. I'll adjust it. So S2 by W, one thing I'll do, and then S2 with respect to S1 I do, and then S1 with respect to W, and and that's all, right? So S0 I don't have to do it. There is nothing further. So my equation looks like, if I write it, that's right. It is with respect to y hat, and y hat with respect to S3, right? Then in multiplication, I have to do S3 with respect to W plus S3 with respect to S2, and then another multiplication that I'll do S2 with respect to W plus I'll do S2 with respect to S1, and then S1 also with respect to W. So this is how I'm getting the recurrent back propagation, right? Uh, uh, so this is much. This is what you have to do for back propagating, and you can see if I do multiplication, I'll get like kind of uh, yeah. Uh, so just forget about this part. Okay, I'll do multiplication later on, but look at whatever we have inside, right? So we'll look into this. So one is we have S3 with respect to W. If I do multiplication here, I'll get S3 by S2 and S2 by W plus this three term, right? S3 by S2, then S2 by S1, and then S1 with respect to W. So this is these three terms are together, right? So to kind of ease up the thing, I'll directly write like S1, and you get it like S1 with respect to W. Okay. So this is how I can write, and and if you can further solve it, the equation becomes the notes. Okay. Just, yeah. Yeah. So to make it like this, I have to. Oh, this is self. This is self. So okay. So so what you have to do is like I can write like one more thing I can write now S3 by S3 here, right? This is just one, and that makes the equation like summation from k equal to 1 to 3 dow S3 by dow Sk, and then dow Sk with respect to W, right? That's what this the whole part here on the right side, the right bracket will become correct. I can call it as dow S3 by dow W, right? So this is what it will become from k equal to 1 to 3, and this is how it will be, right? Uh, do you get it like what I did here? And this is how you have to do the back propagation. Now you have to do same thing with respect to this portion also, uh, with respect to y2, and then you will get another gradients that also you have to sum it up. Okay. For total loss, if you go for total loss, if you think there is one for like understanding purpose, you can take that there is one gradient flowing back. If you understand that much, is okay. I think that's what being explained in this course also. So you'll go with that there is one path, only this much, which I did just now, and this is how you have to do this, right? So if I ask you with respect to loss, you have to do loss with respect to the last uh, this output layer, or S3 in this case is, you can see the from the image, S3 is here, right? Output from the recurrent networks, right? So S3 you have to go, uh, and uh, and then you have to and then yeah, and then you have to write the summation. So this summation from k equal to 1 to 3 S3 k, and from Sk to W, right? So this is how the back propagation works. Uh, and generalize it to, you can write T and T here, and yeah, that's all. So if you want to generalize, you can write it as T. I think this is also a T. Yeah. So this will generalize the formula. Okay. So this is how you can do with respect to W. Now same thing you have to do with loss with respect to U. Okay. Same, almost same thing. There is nothing you can see from the chain that I would have gone here, here like U side, right? So there is nothing much changing there. Uh, and then with respect to B also, there will be nothing much changing there also. Okay. So do you get it? Like back propagation, how does it work? Mhm. Am I audible? Okay. Okay. So if there is no doubt, I can move to LSTM. So one thing you have to remember is how to get the parameters. So this is how you get it. So you get it right. So this is the structure of RNN, and you are going to be calculated like this, and x1. Then this another guy will appear from the previous output which you have to give. So those uh, weights are going to be square metrics. Whatever 3 cross 3 here. Here you will get 3 cross 3. 3 cross 5, and output also will have something like 5 cross 3. So it depends on what is the output size. Here I will choose the same thing. It could be different also, a length. Okay, so it depends on the problem statement. This B could have different size also, not 5 cross, like not 5 neurons required, 3 neurons, 4 neurons required, something like that, right? And C is another parameter, and C size should be equal to the softmax layer, and B size should be of the hidden layer, right? So that's what is. That's how you can get the parameter of any RNN architecture. And the same architecture will use several times to get the all the predictions or whatever, right? So all the structures you can get it. So this is how you get the loss. Now, uh, so okay, so the issue with RNN is this term, right? You can see I'm doing ST by SK. This part is the issue. uh, I'm rolling it for let's say t times, right? So t, if I'm rolling it for 5 times, that means this terminology will multiply again and again for each of them, right? So this term will appear again and again, and this leads to two things. One is exploding gradients, exploding it, or they are vanishing it, right? So and that is vanishing. So these two problems are appearing with RNN. So you can't create actually a larger, or you can't give a larger statement and tell it to predict the next word. It will not work because of this vanishing and exploding gradients, and that issue is in this equation. Okay, so this portion is the equation in back propagation, that where either it will explode or it will vanish. So if they are uh, if they are higher number, then it will of course explode, and if they are small number, then it will reduce to zero, right? So exploding gradients problem, we can solve it by clipping, right? So this thing we can do gradient clipping or something. So we'll say that after a certain point, like some value you can set, that if it goes beyond that, I'll just say it's on, right? I'll not let it go beyond that point. And that's how you can control the exploding gradients, that you can do clipping of gradients. So after beyond certain point, you won't let your gradients to grow. Okay, but with vanishing gradient you can't do that, because they are shrinking and shrinking, and you can't if you put a lower limit, something that it should not go beyond this value, then actually it will not work. Like you can't do that. Okay, so this clipping part will not work with vanishing gradient also, because generally gradients are very small in nature, and you don't want to do that. Okay, so to handle that, this LSTM architecture was came into picture. Now, what they do in LSTM is there are three kind of gates. One is forget gate, one is input gate, and another is output gate. Okay, so there's three types of gate we'll build, and we'll see how this vanishing gradient problem is getting solved by this. But before that, let's see the equation of this. So what happens actually? So you get one uh, x, right? So you'll send not x, but let's say h. I'll use whatever I use in slides. That would be better. Thing that is. Okay. Yeah, okay. So uh, so just consider that there is some h0 coming up here. What is the h0? I'll explain later, because this is something we will always get output from the LSTM. So this from LSTM you'll get two kind of output. One is S ST and another is HT. Okay. So generally we consider ST as a cell state. Okay, and HT is being called as uh, what do they call? So these are all states of the LSTM, right? So one is called cell state and another is called uh, some time step or something state, right? So just state, you can take it for now, and this two thing you will get output um, from the model, right? So LSTM you'll get this two kind of output, and that you will of course give it to the next one, right? So for understanding that, just consider that these two are I'm getting as output. So one thing I'll get is ht minus one here. Okay, uh, and let's say I have one sigmoid layer. Okay, not just neuron, sigmoid uh, layers of that. Okay, like I had in RNN, right? Uh, so I'll give that, and another thing I'll give is xt, so current input, like 1 hot or something like that, and this weights I'll call as u again, and I'll call this ht coming weight I'll call as a w, right? So till now it looks like RNN only. There's nothing different about it. Like this is how RNN was, right? And then it will produce uh something like ST and something, right? So that's how we see that will produce ST, correct? So this will uh, this will produce ST. Actually, it will produce ST, and this is how RNN looks like. Now, what we'll do is we'll have another input from which is coming from ST minus one. Okay, so this is what another input is, and I'll do something called uh, multiplication of this, right? So you can say point-wise multiplication of that. Uh, uh, Sorry, this I'll not call as ST. I'll call it as FT. The FT is the reason that this is what forget get is going to look like, right? So sorry, it's not ST, but it's FT, and I'm getting ST minus one from here. I'll do element wise multiplication here. So this the shape of FT and ST are going to be same, right? So shape or size, you can say they are both are going to be vector of same size. Okay, and I'll do the multiplication here, element wise, and that will give me I'll call it as FT, and this is what Adam at product ST minus one. I'll send it further. Okay, now what I'll do is I'll have another sigmoid here. Uh, you can have 10H or something like that also. Sometimes you will see 10H and all, but for all of them I'll use sigmoid only. And let's say I guess another sigmoid. See, it would be better if I use the image itself. TM image. This looks okay. Mm, I'll use this. Okay, so you can see here. I'll mm, how should I get it here? So yeah, so this is how uh, LSTM actually looks like, right? So this is how really LSTM. This is what LSTM architecture is, and so what you have to do is you'll give x ht minus one xt here, and the weights are going to be u and w for both of them, and you produce a you send it to sigmoid layer, and you get ft from this. That ft and this you can call it as st minus one. You do element wise multiplication, right? So this both the vectors will have same size, and you get here st minus one and multiplication with ft. Okay, same thing. Now you'll send again this ht minus one and xt to this both of this, like so. One is sigmoid and another is tanh, but you can consider sigmoid also. That's what being used in lectures. So sigmoid layers. Okay, and this also you can consider sigmoid. Now, so whatever you did here, right? So it will produce it. So it, and from this 10H, it will produce something like a temporary state, right? So this st, but temporary, not the permanent, right? And you will do addition of this both, right? So here we'll do addition of uh, this first term, and then another term is it, uh, of course, element wise multiplication of st temporary state, right? Then this temporary, whatever the summation is, basically this both two of them will go to this another 10H or sigmoid layer here, and and you will get some output again here, right? Uh, uh, yes. So this mm, what do you call it as OT or sigmoid of S. This is also ST. Now we'll send. think this part is extra. I don't see. Uh, uh, we do. But there are several architecture of this. So let me just confirm that that uh, LSTM is there. Yeah, actually, not this guy, but whatever has been produced here is it's OT and sigmoid of this summation, right? Yeah, okay, okay, I get it. Sorry. Okay. This whatever this summation is, you can call it as ST, and that will go through this another sigmoid neuron, and it will produce sigmoid ST, right? And multiplication of the OT and the sigmoid ST is the HT, right? So another is ST, which is the summation of this, right? So there are three things coming here. One is this portion, which is input gate. Sorry, forget gate. This part is the input gate, but you can say consider all of this as input gate. Or this IT producing is what uh, input gate is, right? Then this last part, uh, kind of all this three things, last three things, you can consider it as output gate. Okay, so this is how this is playing, and if you see the equation of it, you'll realize that how why this is the architecture. So I think in course the equations are being mentioned, that how would they are. So you can see FT, right? So which is being produced here, this blue FT. It looks like sigmoid of WF, then HT minus one I'll take, right? Then UXT plus B, right? BF. So this all of them are F. That's how this forget get is producing FT. Then I'll use as FT and do the multiplication with ST minus one, and it will go. And what will happen at IT, right? So IT is also going to be sigmoid of WI HT minus one plus UI XT plus BF BI, right? Then same thing I'll do with OT. I'll just give you that W uh, O HT minus one plus UO XT UO and then BO, right? So for this, like I have written, like you can see 3 and 3, 6, 9, 9 types of parameters, right? Just from forget input and output gates, right? So this is what gates equation are, and then there is states equation, right? So this states are one I'm doing is like here I'm doing multiplication of uh, this part, and another is like I'm doing the addition, right? So this ST is FT I'm multiplying with ST minus one plus another part I'm doing is IT. I'm taking IT and that I'm multiplying with the ST temporary state. So this is what called temporary state that you have to produce, and this temporary state is actually you got from sigma. You use WHT minus one plus UXT plus B, right? So here this uh, so I this 10H is written, but you can use sigmoid or whatever layer you wish, right? That's not a problem. So if you send your input and st minus one previous ht minus one, you'll get that this st tilde, right? So this tilde is representing that this is a temporary state, and you can get from this the st1, and now you need one more thing, ht, which you want to give as output, right? So this output you'll get from output gate, which you will multiply with sigmoid of st, right? So this st, whatever this st is, will go here to another sigmoid layer, and you'll do the element wise multiplication, right? So this all are element wise multiplication. Now there is one thing that we can consider understand from this is like wf wi wo, uf ui uo, and bf bi bo, right? So this whatever this w's are, right? So w's dimensions uh, are going to be equal, and then these dimensions are also going to be equal. Sorry, u and bf bi and bo, right? So if you know this, you can, if you know one, then you know that others are going to be equal. So what you can do is you can figure out this dimensions, and then you can multiply it with 3, right? So that you can get all the number of parameters using this gates. Now there are some parameter in the states also. So one is this uh, w's, right? Here the this part. So this w's are there, which will also have same dimension as this guys. Okay, there's nothing different about, because you can see they are getting input as ht minus and xt, right? So same inputs they getting, so there will be same number of parameters, uh, uh, and and we'll use same number of neurons. Okay, so we'll not use different types of kind of neurons or number of neurons in this sigmoid. So all three sigmoid will have similar neurons. That's how it works. Generally we prefer same kind of neurons, so that there is no further addition will happen, multiplication will happen element wise, right? So you don't want to mess up with, like, if some one vector is bigger than other, then this element wise multiplication will have some kind of issue, addition will have some kind of issues, right? So that's what this here multiplication is happening, and here uh, addition is also happening. So this uh, thing we have to consider now. Yeah, so what other parameter could be there is uh, from this sigmoid, right? So this last sigmoid is there, and uh, that like naming of that is not particularly given anywhere, like what kind of weights you'll use, but you can see sigmoid, some weights will be there of sigmoids for this guy. Last and that are the last parameter, right? So this four kind of parameters are this. One is from another sigma, that is one more parameter, and if we give it to some output and all, then you will get vc, right? So this four types of you can say each of them, w, u, and v, and then you have sigmoid, so some parameters here, and then v and c, right? So this all parameters will be there that you have to compute to get the all total parameter, right? So you have to sum it up and you'll get total parameters. Okay. uh, Fine. So I guess this guy, if I'm producing O2 of size, and this should be of same size. This should be another. mm, yeah, it should be actually. So what I get it like WF, WI, WO, W, and there should be another W, right? So this is from another this last sigma I mentioned, right? So this, see there are 5 sigmoid you can see here, and this all 5 will have same kind of thing, right? W's will have all of them. This will not have u something, right? So this u part is missing here for that sigmoid, and rest everything will be there. This 4 will have w and u, and b all 5 will have. So that's what is different between the last sigmoid, like here. Okay, so this is how LSTM looks like. Same thing we'll have with GRU. So I will probably go here. Ask, is there any doubt? Anything you want to confirm?
From the W2 once you can say what is that?
W2. So this W2 is coming from. So see, this will have WF weights. Here it will be WI. Uh, Here you can say W, some W weight, right? And this will have W output. Now some weights will be there for this sigmoid neuron, right? That I'm calling as W2. Some weights, whatever you choose. It will not have U. U won't be there because there is no X going there, right? So X is going to uh, this one, this one, this one, and this one, right? You can see if I remove all this uh, drawing, like this, okay? You can see X is going to all of them, but except this 10H. Right, so this 10H and all is written, but you can choose whatever uh, activation function of your choice, right? So we are choosing sigmoid as a activation function uh, for all of them because that's how being taught in the class, and that's why I'm using it. Okay. So this 5, right? So here I'll get WF, WI, some W, here WO, and here I'm using W2. So this W2 is for this another sigmoid. Will not have U. U won't be there. This guy will have UF, UI, U, UO. There's no U. Then there is will be BF, BI, BO. Here also B, and there here also B. So this one thing is missing from is U. That's all. Otherwise, nothing is different. And all of them. So all 5 kind of things you are seeing here, all of them have same direction, same dimension. So W, if I'm saying W, all W's have same dimension, all U have same dimension, all B have same dimension. Okay, fine.
Yes, sir.
Okay. Okay, so now we have okay. So one thing which we do is after this, so you can see HT is going somewhere. That thing we use for prediction. So we'll send it some VHT plus C, and we do softmax over that. Okay, and this is what we'll call as Y hat. Okay, so this is what happens after we get this, and then the CT, right, will become input to itself, right? So this will go as input, and this will of course go to input, and here some new XT plus 1. So that next guy will come up here, right? And that's how this time step across the time step this LSTM will work. So this is for t equal to 1, and for t equal to 2, this whatever we had will move forward. Okay. Now same thing we are doing with GRU. Before going to GRU, let's see one thing, that how it is able to handle vanishing gradient problem. So the thing with vanishing gradient problem is that it is vanishing across all the paths, right? Now, if I uh, uh, if so if I do back propagation across all of them, uh, the point is that across this path, right? So this path is there, this path. So in that path, the back propagation, if I do, then it will not vanish. It will not let it vanish. So this path will protect the vanishing gradient problem, and that's how it is able to handle the vanishing gradient problem, and it is able to, you can give more and more words, but this is the path across which it will not let it vanish. Okay, I can go to slides and explain it, but it is it's a little difficult. Okay, so let's not go there. If you want to understand, maybe you can go to the lecture and try it, but as of now I'm not feeling we should go there. Okay, so but this is the path which I wanted to show, that it will help in not letting it uh, completely vanish. Okay, so now let's see what we can do with GRU. So GRU architecture, diagram, whatever. Uh, this looks good. Okay, we can use this. Uh, Date get. I don't see this as a GRU. Mm, um, mm, date. Mm, this sounds good. Mm, okay. This okay. 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 Yeah, we can.
Is publication not working?
No, it is working. It is, yeah. Okay, so yeah, so now we'll see what is with GRU. So same thing, like you just have to just know the architecture. So if I give you the architecture, I think you will be able to figure it out. So okay, now hmm, oh, glue. So this is what x t is. Here I'll give h t minus one. So now you'll have only one equation, which is h t. Or actually, if I go with the Sir's equation, then that would be st minus one. Okay, so let's use that st minus one xt. Okay, it's going there. Now it's coming to this sigmoid, right? So this called reset gate, and the another gate is update gate. So now we'll have two gates only. So uh, so what do you think the first equation is, right? So let's say if I ask you, can you give me this reset here, right? So here, can you give me the equation of that? What will happen? Uh, you need one weight for this guy, one weight for this guy, and one bias. So what do you think will happen? Uh, so I'll do sigmoid of say I or input gate. I can call it as input and then another as output gate or something like that, right? So I'll call it as I, uh, or is it mm, hidden state 1 minus t 4t. I'm multiplying the bus t minus no wait oh, t. Yes, okay. So this is what wi, then I'll multiply it with st minus 1, right? So whatever coming from there plus uxt is going from here and then bo. So this is what equation of uh, the update kit. Now I have to do element wise small. So whatever wherever you see x plus and multiplication, everywhere we are doing element wise. Okay, so multiplication is also element wise, addition is also element wise. Okay, that's what we will do. Uh, now what's going here is you can see this xt is going there. Okay, and mm, and I'm getting out from here and I'll do um, multiplication of that. So uh, okay, let's see what we can do. So this hidden state, why there is I'm doing the is it coming the way around? I think I get it incorrect. So this is part correct, but the other part is uh, not that way, but this way, right? So I'll do whatever is this is OT. I'll do OT multiplied with ST minus one, right? So this will produce uh, OT and ST minus one, and of course XT is also going here, right? So both of them will go here, XT and OT multiplied by ST minus one. Okay. So here XT going inside of this another neuron, and I'll call it as in why it become OT. Okay, so I think I messed up the weight. So this should be O, and this should be also O. Okay, like now another is VWI. Okay, sorry, OI, which I'll call or it's called as IT. Yeah, IT. So I'll use sigmoid. It's going here. Now I'll produce WIST minus one. Yeah, plus UXT plus BI. Right. So I'll get that. Now I'll get mm, uh, there's one temporary hidden state which I'll get. So the sigmoid of W, and so this I have sent, right. OT and uh, element wise multiplier ST minus one will go there. So OT and element wise multiplier ST minus one will go and multiplied with W thing. Then UXT minus will come plus B. Right. So this is what temporary state is. So for this part here it is producing ST temporary state tilde. Okay. Uh, yes. And here I'm producing IT. Right. So this whatever this production is, like before one minus it's IT. Okay. So what we are doing is we have this IT will reduce like one minus IT. Okay, one minus IT. So how can you do this one minus IT? Like what do you think? Like what actually you imagine when I write one minus IT? Uh, any comments here? Like what do you imagine this one minus IT is going to be? Uh, let's say IT is let's say IT is 0.2, 0.3, 0.4, 0.1, right? So what do you expect one minus IT will look like? Uh, anything? Mm, okay, so one minus IT will be like what you'll do is you'll subtract this. Okay, whatever you get is this one minus IT. Okay, then you'll do element wise multiplication with ST minus one, and and there's another which is you'll do IT and element wise multiplication of ST temporary state, right? So that's what is happening uh, at this point. So what you got from here is one minus IT, and that you are multiplying with here. So due to this multiplication, you are multiplying with ST minus one, which is coming here. So this two will get multiplied, and then you'll do addition. This guy with the IT, and so IT is going here also, right? So this IT and something coming here, which is temporary state, which are getting multiplied, and here the addition is happening. So this both of this two will come out from here, and this two will be from here, right? So that's how the addition and multiplication going on. So this is how the GRU architecture is. So we don't need any you can call forget input output it. So forget get we don't require it. Uh, this being taken care in this input get, right? So this gate, update get, will actually uh, convert or handle this forgetting part like that, right? So uh, we don't need it. And this is how GRU works. So if I write GRU equations, it's gates are like this. The gates are, one is OT, that is sigmoid of W st minus 1 plus U xt plus B, and IT, which is sigmoid of, you can call WO, which is WI. Okay. And states will be, one is you will get hidden state. Sorry, one is temporary state. So this you will get W, then you'll multiply with OT, which you got there, element wise multiplication with ST minus 1 plus UXT plus B. Right? So, so we don't expect you to remember this equation. Like they are not um, easy to remember or something. But what I uh, what we actually want is you should know that this how these equations are and what they do, right? So this BT, or sorry, not BT, but ST tilde. Okay, so this guy is going to be a vector, same as this guy should be a vector, 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 vector. Then this W is not going to be vector; it is going to be a matrix, and OT is going to be vector, vector, matrix, vector, vector, right? Metric something. So if you know this, you kind of understand how multiplication works, how it's going in, and how does it work, right? Like that much is expected. Like how do you calculate the parameter, right? So this you have this W's um, output uh, parameters, then input parameters, and then there is one hidden state, so a parameter for that. Or you can, if you remember this images, then there are three sigmoids, and all three of them have uh, not all, but this two will have UWB. This also will have UWB, and this guy will have WB. Will not have U, because oh no, I think both of them are going here also. So I think yes, UW and B for this guy also. And so this three kind of weights are playing into the picture, and they are creating this GRU architecture. Okay, this will produce ST. So the produce ST, and it will go to the next time step. And you don't have to understand backprop for this, but generalize, just think that backpropagation is happening, right? So this is a recurrent. This whole thing is a recurrent now, and it will go to next. Then you'll do the backpropagation. So this ST you will use for prediction also. Okay. Uh, so that's how GRU works. Now comes the encoder decoder. If you have a doubt, you can ask before that. Um, Otherwise, I'll just go through the slide for this. Easy. So now what we have to do is we uh, okay. Uh, but okay, so uh, uh, encoder decoder. Before I mm, So the idea of encoder decoder is that we have uh, we have this you know let's say one RNN is there, and you're using that to predict the next word. Okay. Uh, now the issues what happening is that it is having the issue of uh, vanishing gradients and all and which can be solved using LSTM. So if you use LSTM cell, then you won't have this problem, the vanishing gradient. It will handle that part at least. Okay. So and same with GRU also, I think so. For a GRU, explaining why it's not vanishing is difficult, but this also have that thing like it will also not have vanishing gradient problem. Uh, but now what we did is like we will have one model RNN which will encode the values like it will produce a vector, let's say ST, and then we'll send it to another RNN. Okay. Or LSTM, you can even consider anything, and that will send as a LS uh, as an input to another RNN along with the values we wanted to predict, right? So this what we can, if we do, then it seems the accuracy or whatever you call the scoring is coming out much better, right? So that's why we come up to this encoder decoder model. So this initial part we do first encoding, and this next part is called decoder, right? So the uh, yeah uh, yes, right. So in this way, the thing is like now earlier we were restricted to the part of let's say words, right? Like sentences or something like that we can give. Now we can give input as image and in encoder decoder, text, speech, anything, right? So speech, anything you can give. It just we have to do some pre-processing earlier, and and that will help in RNN and then encoder, and then we can get it to the decoder part. So that's why this encoder decoder model become popular. That you can use all the problem set which you have, and you can apply encoder decoder on that, and it will produce a good output. Okay, it will produce good results. So let's say this man throwing a frisbee in the park, and this image you have. So what you have to do is you want to give this, right. So what you will do, mm, you want to give this as an input to the, you can consider LSTM RNN, take sentence given an image. So this is my input, and I want this as the output, right. So this is what a problem of uh, yes, context or text generation or something like that, right. So mm, okay, so not, so we'll give this we can give this image as a s0, and then we can have this all the vectors which you can go like go, or this is what I wanted to predict, right. So I'll send go, and it will produce first a, then in second time step it will produce men, then in third it will produce throwing, fourth, and then stop, right. So we'll have all of them, a sentence being produced like this. So this is how the training will can happen, right. uh, Still we are not at encoder part, but uh, uh, don't see much time spending here. uh, yeah, like this. Okay. So so we'll give this image to CNN will produce some kind of output. So you have to use the fully connected layer. Okay. And what we have seen is this, let's say this is RNN. So RNN has equation of first let's see what is ST. ST is sigmoid of U X T plus W ST minus 1 plus B, right? So this is what equation is. Now we know that uh, this ST minus 1, right, should be of the shape of the neurons in the hidden layer of RNN, right? So we have to make it of the shape of whatever this neurons are a hidden layer, right? Then only I can give it as ST or S0 here. So if I have output of size 1028 from encoder, then I have to use another hidden layer which will produce the output of whatever this S0 was expected, right? So this thing I'll do, and I'll get this as input. And the further training is as we used to do, and then of course it will do the back propagation till all the parameters in CNN. Okay. And that's how it works. So this is how the encoder decoder architecture works, and you can do for everything. For example, the next is, let's say, text entailment. Okay, image captioning. Now another is, let's say, textual entailment. So given a premise, you have to do some hypothesis, right? So for example, hypothesis, it is raining outside. So based on that, it is predicting that okay, the ground is going to be wet, right? So this is what textual entailment. So some context you give, and it will think in that direction. So so what you will do, you'll produce one encoder. You are given training is outside, and it will produce the last vector, which will comprise of all the information till now passed to it. We'll give it as input to the decoder, and and we'll say go. Right, so it will go, and it has started producing the output. I will feed it here. So here something we are doing different is called teacher forcing. Okay, teacher forcing. So teacher forcing means that's a the I got here will be probability, right? Like it will be like 0.2 to 0.1, 0.33, and like this. So the summation will be 1 of this all the, because the last was softmax layer. But I'm not going to give that here. Like I'll not use the same output here, but I'll use a, let's say, the true output, right? So I know that the is written like this. So I know it, right? So that's why I'm using uh, I'm going to use that here, right? So that whatever the next is, I'll use that. Like you can see 001 or like this. Right? So the is being written like this, and that I'll give. I'll not give this softmax output, but I will do this true output. So let's say my even if I do a mistake here, I get a different output here, not the, but ground itself I came here, but still I'll give the here only. Okay, so this is what called teacher forcing. So we'll always give true outputs here, not the predicted output. Okay, the true outputs are going to be one hot vector only, one hot vector, or embeddings you can consider. So if we use embeddings, then this are going to be embeddings, not the probability which we got here. Okay. Now, so this is how encoder decoder works, and we have like everything in place. Like you can see, we have uh, equations like this. So RNN, you will give HT minus 1 XT, and you'll do all this uh, encoding part using RNN. You'll give HT whatever you got here as a input to the decoder, and then same thing you'll do with RNN. And you can see here I'm using ST minus 1, and this what is YT minus 1, one hot vector, right? So this is what I'll do. So this is what this part is called teacher forcing. Okay, that I'll force it to learn the correct way. But while predictions we don't have. So while predictions will not do this, but whatever the predictions we get, right? So while when in test phase, test set we have. For test set, we don't have the output. We don't know what is the next word going to be. So that time I will have to use the actual predictions, right? So probability or whatever I get, I'll use that. Then I'll use softmax, which I'm calling as probability uh, given by t minus 1. What will be the next word? And x, right? So this using this 2, I have to find the probability, and that's what the softmax is actually, right? So loss is again the cross entropy. There is nothing new here. U decoder, V decoder, W decoder, and now that's what we are calling. Currently it's RNN. So uh, so UVW is fine. Uh, yeah. So I guess they forgot B encoder here. B decoder. Okay. That's what. So this all parameters will be there that you have to update, right? So this currently RNN, but you can use LSTM also for this basic unit. So this basic unit you can use anything, LSTM unit or GRU unit, as you wish. Okay. Same thing will happen for all the like many problems. Like what is this? This is like machine translation, right? So if I give you I'm going home, and translation English to Hindi is मैं घर जा रहा हूँ, then you can do that. So you'll give you'll use RNN and another is RNN. Okay. Now same problem set. There is nothing different about it. Now what is this? Trans iteration? Okay. So basically you write India as India only, but in the Hindi statement. So sometimes some words have like they are from not the original language, but they came from outside, and we use it like cricket. Uh, there is no there's no word for cricket in Hindi. We have to use that only, right? So like cricket or whatever. If you understand Hindi, so likewise we have to write India then like this. So what I'll use as a encoder? Uh, any I don't want to say it like what I'll use as encoder. What I'll use as decoder. So encoder I'll use RNN. I already said showed it. So what I'll use as decoder here. What do you want as a decoder this unit? Uh, mm, okay. I'll use RNN only, right? Like, there's nothing new about it. Like decoder is also RNN. So I think you get the point. I don't see any point in explaining this. So if you go through the lecture, sir has explained it well. So if you have images uh, with sequence, then you have to use RNN of CNNs, CNN and then RNN, and then you can do it, right? So I guess that's what encoder decoder is. So I now explain what is attention mechanism, right? So what is the issue with current setup and why we need attention? We'll go there, and I'll just complete the session. Okay. So the issue is, let's say I have this मैं घर जा रहा हूँ and I'm translating it to English, Hindi to English. Uh, the issue is like at a point, right? Let's say I want to predict I. If I have information about me, if you understand Hindi, then these two are related words. Then it would have worked, right? So if I have weightage or if I somehow I know that this is what the important word is, it would be good. Like so, the problems are that which word is important if I know somehow, right? So that I don't know at a timestamp, which is the input word is important that I don't know. So I want that somehow. Um and another is that how much important, right? So how much could be there? Like sometimes maybe two words are important. So two words can let's say ja raha, right? So this ja raha could be related to going. right? So these two words are important. So it's not necessary that only one word is important, but two words could be important as well. So uh, how many word, which word is important, how much. So that thing we need. And sometimes what happens if I tell you to, let's say, do uh, translation of this sentence, or this three sentences written here in your native language, whatever you choose, you can do that. You can try. You can give uh, maybe 1 minute, and uh, 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 okay. So what kind of difficulty you would have felt while doing the translation? One is like, you would have forget which one should I go, like what is the important word, right? So generally when we do the translation, what we do is we go with the important part of the word, that let's say attention or task or something like the encoder is the important part here. And like encoder is the important part here. So as I'll build my sentence around it, right? And I'll forget mostly what I have written around it, right? So something like that. So uh, the attention span or focus of a person is limited, and that's what we also do. So same thing we have to do here. So we have to build this attention mechanism, that this word is important, and we will give that value, right? So that thing we have to do here. Now how will I do is something very you know fancy. So I have one encoder. Okay. Let's say this is a decoder and another is encoder. Okay. So I'm getting four thing. मैं घर जा रहा हूँ. Right. So five words I'm getting here. Four words I have to give as a output. Uh, now now you can convert all of them as one hot vector as of now, and then you can give inputs to that. So let's say I get one thing as a output, and uh, yeah, okay. So as I'll give this as one hot vector, so 1 0 0 0 something like that, and 0 1 0 0 0, and so on, right? So this is how it will be there. Now the output which is being produced here, I'll call it as ht, right? Now so and same thing I'll do here. I'll give some kind of ht minus here, and here I'll call it as what are coming here as ht. So this whatever the input is, it's going there. That's what ht is, encoder decoder model. And now I'm calling this as s1, s2, something like that, right? So this is going to be h1, this is h0, this is ht, uh, whatever you get, 5 in our case, and h2, something like that. So this equation and all, if you write RNN and all, you will get it, right? So that how you can write the equation. Okay. Hello. Am I audible?
Yes, sir, you're audible.
Yes, sir.
Okay. Okay. Uh, okay. So now we wanted to predict that which word is going to be important for each time step, right? So here I want to predict. Uh, I want to know which word is important here. So what I can do? What what is the thing I can do is I can give all the words to the uh, this one way, right? I can give all the words to this input and let it figure it out which one is important. Um and and that is the idea actually that I'll give all the 5 words. So first encoding part is done, then only I will do it, right? So first I'll do this encoding part. I'll have ht and all the things. So now I want to predict it. So what I can do is I actually need some kind of function which tells me the importance of uh, this h, all of them, like let's say I'm calling this as j or timestamps or whatever you call. And here I'll use t as a timestamp. So I want all the h, j, and at at first timestamp. So first timestamp is, let's say, uh, t1 or let's say s1, right? So s0, or you can call, here I have s0 from here, right? So this ht is actually s0. So if some function is there, or something, right, which tells me that importance of this two, right? So that all the h, j, like 1 2 3 4 5 and s0, what is the importance in between them? I get, if I know that, then my attention work is done, right? So this is what I my idea is, that I have this 5 words which is important, I want to know it. So what could be a good idea, or what could give importance to each word is, I can use some numbers. So let's say a number which tells me that this, let's say 5 vectors are there. Ju- just for example, you can take 3. This is important by 0.6. This is important by 0. Maybe 3. This is important by 0.1, right? So if I have these values, uh, you can say that it is doing the job, right? So if I have, let's say I want to write go, right? So maybe this is ja and this is raha, right? So these two could have explained go in self, uh, in attention thing, right? So I can say that I give more attention to ja and raha. This could be who or something, and it's little irrelevant for this word, right? So this prediction of this word, but still it got some value. Okay. So this is how I want something, that some function will be required to do this. Now, what could be that function is, and what uh, the researchers find out, that why should I, waste my energy? I can use a neural network, which is a universal approximator, right? So we studied universal approximate theory in first, I guess, third week or something, that you have this kind of function. You can approximate to any extent, let's say like less than or greater than eta or something, up to that extent, if you use some neurons, right? So that was universal approximate theorem, that you can predict any function. So why should I spend my this time finding that function, the real function? But what I'll use some weights. I'll call w attention, some weights, right? So this weights, I'll use more weights like u attention something, and then I'll create a neural network which will give me this attention, right? So this attention's value will I'll get from there, right? So so that's what I have to do. So I have 5 words, right? मैं, घर, जा, रहा हूँ. So this 5 words are there. I want to predict my first value, or first attention value for this. So I'll give all 5 of them or to a neural network. So I'll draw a neural network here. It could be of any shape. Okay, so it doesn't need to be 5. Let's say 3 one. Okay, I'm going to give this. So what will be this? I'll call it as, I don't know, U W attention or something, right? So W attention you can even call. So what is the dimension of this?
3
Uh,
cross 5.
no. Neurons are 3 only.
3 cross 5.
No, it should be 5 cross 3. 3 cross 5. 3 rows, 5 column. Okay. So 3 cross 5. So I'll send this. I'll get something as the output. Okay. I'll now the thing is I'll whatever I get as output, I uh now I need the uh I can't use this, right? So these are currently independent of each other. I need some probability distribution which tells me that which word is more important. Let's say this word is more important, then we should have higher probability value. So what we always do with probability is related to softmax, right? So whenever this probability issue comes up, we always use softmax. So I'll use another layer which is of softmax, right? Uh, which is of yeah, correct, softmax. But I need 5 neurons in that because I uh, yeah, 5 neurons in that. So it will tell me all the values for 5 of this word, right? So one word, 3, second, third, and fourth. That this much important they are. So I'll use them like this. Okay, a probability value I'll get for all of them. So first one is related to this guy, second, third, and fourth and five, like that. Okay. So this part is softmax. Here it is. And if I write a equation of this, so this is called F attention, and you can see from the slide as well that the equation values are um, okay. I'm not sure what they use, but if I can just go down, attention is all you need here. Yeah. So this is what the equation is, right? So this is what attention equation is. So we use U attention with all the HJs, right? So we have all the HJs. We used U attention for that. So U attention, okay, and all the HJs I'll give there 1, 2, 3, 4, 5 in this case, and it will go here, right? Like this. So you can send this the whole matrix thing here, and and you will uh, so this multiplication and then some kind of bias you'll require b u attention at j plus yeah. So okay, so one thing I missed is we'll use whatever previous time term, right? So s0 in this case or st, we'll send that also here. Okay, so that thing also will go not there but in the neural network, like initial thing, right? So S0 and HJ both will go. So that will be W attention and S T, right? So whatever timestamp you can choose, T0, but it will be not previous only, okay? So if I'm finding my attention here, then this S0 will only go, and all 5 of them will always go. So for all of them, like when I'll compute uh, attention here, all 5 will go, but S1 will only go there, okay? Like that. So and plus some bias you can choose. So a sigmoid you apply over that. Now I'll use that whatever value I got from sigmoid, I'll multiply with V attention, and then the sigmoid of whatever you call here you got. and I'll call that as a attention. Okay, so this is what attention looks like, and the symbol used for that is uh, EJT. So sorry, this is not attention. Like EJT, you'll get the attention, then the sigmoid of whatever you call attention. This this thing, right? So whatever I wrote here, you apply softmax over EJT, and you get alpha JT, which is softmax of that. Okay, is it fine? So I'll get alpha JT. Now there is something more I have to do. So see what I found as of now is alpha JT. Basically, alpha will look like this 0 point some probability value, right? 0.1, 0.2, 0.3, 0.3. So maybe 3, 2 or something. The total should be 1, 3 plus the 6, 8, and another 0.2. Okay, so something like this. So I found this probability of each of the words. Now what I have to do is I have to find CJT, right? So see, the CJT is summation of alpha JT, uh, multiplication of alpha JT, which with H uh, J. Right? J is the I'm using for encoder, and T I'm using for the decoder, right? So for J will go from 1 to whatever numbers are there, uh, right, at each timestamp. Now this is what CJT is the value which you'll get. So what do you think the value of uh, what do you call uh, uh, what do you think the shape of CJT will be? A vector, a matrix, or something like that? Uh, if you see this will look like H0 and alpha 0 1 or something like that, plus alpha uh, 1 1 and H1 plus alpha, or I call 1 0 2 2 0 3 0 and H3, right? So this is how this will go, and it will look like a vector only, right? So the CJT will also be a vector, and this is what is a attention thing, right? So what you will do next is you can see from the equation that I'll use the CT, which I found now, that I'll give CT also as into the RNN. So this RNN now have two kind of input. One is from the X. Uh, so in decoder we'll have one from the this one hot vector, right? So that's what mentioned as E y hat t minus 1. So from previous, or you can say one hot vector. One you'll give a CT, which we just now found, and st minus 1 was always going there, right? So we'll have that also, and that's how it works. So that's how you can do the attention thing, right? So this is how you can add this attention component to the RNN. So now this RNN is attention based RNN, right? This one more component or one more vector you will give to the RNN, right? So RNN architecture was like this. We initially decided. Uh, so one more. So S0 was going in the first time step. Then now we'll have Y0, and then the C1 or like that, right? So C1 will appear here using this formula, and will go there, right? So this three kind of inputs will go into the RNN, and of course the RNN will have one more layer of output, uh, and so on, right? So this how the attention works. Okay, so this parameters now coming up is decoder V WC like this, and now U and V attention is coming up. I think W attention is missing, but that thing is also there. Okay, so this three or six, I don't know, 9 types of parameters you have to handle now. In encoder, we don't do the prediction, so there is no V encoder. Okay, only V decoder is there. So V decoder is only there. We don't do any predictions here. Okay, only all the predictions will be here. So here we'll just convert, or we just want this vector, right? So final HT is what we are interested in, which we're going to send it here, and then rest of the works will work as it is. Okay, so that's all I have. If you have any doubt and attention, you can ask, like, uh, anything. I don't know. But this attention is another uh, neural network. Okay, this attention is another neural network from which it has to go. It will produce the output of that uh, vector kind of thing that you have to multiply like this. So this are containing the importance, you can say. These are the importance, you can say, and then that you have to multiply with that words vector, and then you have to sum it up, all of them, and you get finally you will get another vector which you are calling as CJT, right? So C is the word you are using for that. Okay. Uh, yes. So that's all we have today. If you have any doubt, you can ask. Uh, uh, After all of those are done. Okay, I guess there are no doubts. I can stop the streaming.